everyone, welcome to this 13th lecture of our course on blockchain and its applications. And today we will start a particular topic which we have named as blockchain elements, where we will introduce you some of the basic elements of a blockchain. In general, in this discussion, although the concepts will be for any kind of blockchain, but specifically we will be focusing on Bitcoin because it is easier for you to follow and also understand, and there are a lot of materials which can available online which you can easily make use of. So, this is blockchain elements 1. So, the concepts that we will cover in this lecture, this includes what is meant by blockchain. Of course, we already understand what is meant by blockchain, but we will effectively introduce you in very simple terms. We will show you how the blocks look like in a blockchain, and then we will first focus on the concept of block headers. So, the keywords for our discussion in this lecture, these are block structure. We will see the structure of each block. The block header, as I mentioned, it is very important and it is really something that is very interesting for us to understand. And then we will talk about what is meant by this term of mining a block. This is very important because the whole concept of so called security of data in blockchain, that means once some data has been put on the blockchain, it cannot be easily be tampered with. That is the fundamental concept which is based on mining of a block, and in that process we will also talk about block generation puzzle. If you remember from our discussions on this puzzle friendliness property of cryptographic hash functions. So, here we will see realistically how this block generation puzzle that is solved, and we will also ensure that you get a good feel of how things are done by taking examples from live Bitcoin blockchain. So, that is what we will do, and you can also repeat the same yourself as you are going through this particular course. So, it is just a matter of repeating what we have said before. What is a blockchain? Indeed, it is a platform for executing transactional services, various types of transactions, like Alice sends 5 Bitcoins to Bob and Bob then sends 2 out of those Bitcoins, 5 Bitcoins to Carol, and so on. So, these are the different types of transactions. Also, remember that in blockchains, we can also support transactions which can lead to, say, certain operations in the real world. For example, if a blockchain supports, or maybe say a particular state in a country supports this kind of processing, like say I have a vehicle, and then as long as the vehicle is owned by me, I am the title owner of that vehicle. I sell it to somebody, say B. In that case, that so called title of the vehicle will now be transferred to B. So, what can be done is that if I make the payment using blockchain, say using Bitcoin, and B says, okay, I have received the required number of Bitcoins, and then the next transaction, that is transferring the title of that car or vehicle from me to B, that can also be carried out. So, that will also be another transaction. So, overall the idea of using blockchains like Bitcoins and of course, others like Ethereum and so on, these are to ensure that certain transactions can be carried out, which could either be the cryptocurrencies of these different blockchains, Bitcoins or Ethers in Ethereum, and that can also lead to some more operations which can cause something happen in the real life or in the physical world. Okay. And this blockchain, could be spanned over multiple organizations or individuals who very importantly may not, or at least they need not trust each other. So, even if they do not trust each other, it is possible that we will have the operation of the blockchain going, and it is an append-only shared ledger of digitally signed and encrypted transactions replicated across a network of peer nodes. So, that already has been explained to you what is meant by a peer node and how this what is a ledger, and now we will see that how digitally signed and encrypted transactions can be replicated across a network of peer nodes, and these peer nodes are running on different people's hardware. And then of course, as said in the second bullet, that they need not trust each other. So, what is a block in a blockchain? So, if you see here that a blockchain, as we have seen several times before, it is a chain of blocks, and these blocks are connected, that chaining is done using what we have studied before as hash pointers. Okay. So, each block, as we see here, so let us focus on one of these blocks. So, this whole thing is the blockchain, right, and out of that, this is a block, this is another block, and this is a third block. In a block, what we have is that we have these two parts. One part are these transactions, and the other part is the block header. Okay. So, this is the block header, and these transactions are what? As I mentioned, that these could be Alice paying 5 bitcoins to Bob, or Bob paying 2 bitcoins to Carol, or transfer of title of my vehicle to party B, and so on. These are the different transactions which are there. And the block header part, that contains some more information which is actually used to link one block to the next. So, we see that the first block is 51, and this 52 block actually is using this hash pointer, which is pointing to block 51, and thus connecting 52 to 51. And similarly, this arrow here, that is the connection between block 53 and block 52, and likewise we will have other blocks as they keep added to the blockchain, and blockchain gets longer and longer. And these transactions that we have said, these transactions are what we call verified by peers. So, if in one node the transaction is carried out, so Alice makes a transaction, and then that transaction information will be actually spread out all over the blockchain, and all the peers which are the other nodes in the blockchain, they will be so called verifying those transactions, and later on we will also see what is meant by verification of these transactions. Now, the cryptographic security, the entire security is provided by cryptographic techniques, and those techniques are the ones that we have already studied in our this course earlier. So, they ensure that participants, they can only view the information on the ledger. So, this whole thing is called a ledger, and assuming that they are authorized to see. So, there could be certain blockchains where we can also ensure that only a selected group of people can see the transactions. In other blockchains, it could be a public one, means everybody can see what is going on in the blockchain. You yourself can actually join the Bitcoin network or the Ethereum network, and then you can see all the blocks. And in fact, we will see that even if you do not join, on the web itself you can also see all the blocks that are getting added in the blockchain like Bitcoin. Okay. So, this particular figure has been taken from this source, and you can also go to this site to get some more information. So, structure of a block. So, now let us look at the structure. The block is a container data structure. You know, from basic data structures concepts, you have different programming skills, and you have seen what is a container data structure, and it contains a series of transactions that we saw here. It contains a series of transactions like the ones which are shown here. In Bitcoin, so now as I said that the concepts are generic in nature, but we will talk specifically about Bitcoin, so that the understanding can be much clearer, and you can extend the same concepts for other blockchains also. In Bitcoin, a block may contain more than 500 transactions on an average. So, roughly there are 500 or 1000 somewhere in between the transactions. It is more important that it is not the number, rather the size of a block. So, this block that we talked about here, what is the size of a block? The size of a block is around 1 megabyte, and this number was set by Satoshi Nakamoto. You have heard about Satoshi Nakamoto in our earlier classes. So, Satoshi decided to go for a block size of 1 megabyte. There have been a lot of discussions, conflicting views on this, whether the size of this block, each block in a blockchain should be made higher, like say 8 megabytes or so. Now, larger blocks, why people would advocate for larger blocks? Because they can help in processing large number of transactions in one go. Of course, that is very simple to understand. If each block is of larger length, larger size, then more transactions can be included in each block. But of course, it will take more time for verification and propagation. So, we may have to wait for more transactions to arrive, so that the block required block size of 8 MB is reached, and only then the processing, subsequent processing can be done. So, the latency will be up, but once one transaction gets included in a block, so lot of such transactions will be there. So, once a block is generated, lot of transactions will get included in that. Okay. So, here as I mentioned, there are two components, one is the block header and the list of transactions, and here we have given an example of the block header. Of course, you might not be able to see it clearly, and that is the intention. It was done intentionally, because you do not really need to see it here. What we will do is that we will go to the different websites where we have all these blocks. So, let us go to one of those websites, which is this one that I have clicked, the first one, which is the btc.com website. And then if we see, so this is the interesting part, the reason why we wanted to show it here is that here in btc.com, this site actually this shows in real time all the different blocks that are there in the Bitcoin network. Okay. So, if you see here that this at 1643, that is at 443, the Bitcoin block number 703823 was mined, that means this block got added to the Bitcoin blockchain. Then at 450, 703824 got added, and then if we just wait for a few more minutes, you will see that more such blocks are getting added. And here what you can do is that you can always search for a particular block. So, if I say 100, so that means what it will do is that it will search for this Bitcoin block number 100. If I click on it, you get Bitcoin block number 100. So, you see here this 100 is written, so which tells me the block number in Bitcoin. Okay. So, that is the reason why we do not really need to worry about what we can see here, but you can see that this is 697125 is the number. So, if I just type it in 697125, just let us make sure it is 697125, and then if we search for it, immediately we get this Bitcoin, this 697125 block, and what you see here is exactly what is shown here also as the as this particular block here in our figure. Okay. So, what is important is that in our discussions we can go to this btc.com, or you can also go to this blockchain.com/explorer, where also you will get the same blocks. Okay. So, either you can go to btc.com or you can go to blockchain.com, and here again if you see that it is also showing the same set of these blocks in the Bitcoin network. Okay. So, these are interchangeable, you can go to one or the other, and you can see that they are also generating the same set of these blocks. Okay. So, you can familiarize yourself with navigation to these different sites, that is btc.com and blockchain.com, and then get to see the details. So, the block header. So, in today's lecture, this first lecture in this series, we are going to focus only on the block header part. Okay. And then this looks like this, that we have this block, first block, second block, and so on here as is depicted, and then this is a first block, say H0, and then H1 which is connected to H0 like this, and so on. Finally, H4 is connected to H3, which we have seen many a times before. So, what is done is that metadata about a block, so that includes previous block hash, some mining statistics as we will see, which is used to construct the block, and the Merkle tree root. So, you remember that the transactions are organized in the form of a Merkle tree, and then pairwise the transactions are hashed like this. Say if there are say 8 transactions, first 2 transactions are hashed, then third and fourth are hashed, fifth and sixth, seventh and eighth. Now these 4 hashes that we get, the first pair will be hashed and the second pair will be hashed, and those 2 hashes that we get, they will be finally hashed, and the one that we get will be the root hash, which is the root of the Merkle tree, and that Merkle tree root, as we call it, that will be also kept in the block header. And then what is the reason for previous block hash? As we have seen here in this example, and also we have seen before, that the purpose is that if some adversary tries to tamper with the data in any one block, then that adversary will have to change all the block hashes till the latest block. So, if say the latest block is block number say 700,000 and the adversary wanted to change some transaction in block number 600,000, then all these 100,000, that is 1 lakh such blocks, all these hashes will have to be updated by the adversary, and it is very difficult, as we have seen before, due to the restrictions that are put on the generation of the block hashes, that is number of leading zeros, as we have discussed. So, it will be very difficult computationally to recompute the new hashes for all these 100,000 blocks, okay, because if you change even one transaction in say block number 600,000, that would mean that you will have to recompute its hash, then recomputes the hash in the next level of the Merkle tree, and then the next level of the Merkle tree, and all the way to the root of the Merkle tree. The depth of the Merkle tree will be dependent on the total number of transactions in that particular block, and then that Merkle tree's hash, that is the Merkle tree root, is there in the block header, and the block hash that is computed, that makes use of the Merkle root hash also. Okay. So, then changing any transaction will mean that the root hash of the Merkle tree will be changed, and then that will also affect the block hash of that particular block, and because that block hash is used in calculate the block hash of the next block. So, the next block's hash will also have to be recomputed, and so on and so forth. So, from 600,000 you have to change the block hash of 600,001 and then 600,002 all the way up to 700,000. So, each of them actually is computationally very challenging. That means, computing so many such block hashes will be really difficult unless the adversary has a lot of computing power, but it is assumed that the adversary cannot typically have that much of computing power, and that is what makes the blockchain tamper proof. So, this includes solving the blockchain block generation puzzle. So, we talked about this puzzle friendliness of hash functions. So, you see here in this particular example that this is one block, this is the second block, and this is the third block, and then this is the block header. Okay. So, the transactions of the blocks are not shown here, because we are focusing only on the block header. If you see in the block header of the second block, we have this previous hash, which is same as the block hash of the immediate previous block, which is there in the header of that previous block. Okay. And then the block generation puzzle is that we have to find our nonce. These nonce, as we said, and we have seen through some illustration in the website supporting the textbook, is that how to find the nonce which would generate the desired hash. That means, it will contain certain number of leading zeros at the prefix. So, this is what is an example that so many leading zeros should be there as the prefix, and this is what is going to be making it very challenging. Now, if we consider that how exactly this is done, what is there in the block header. So, this mining, the term mining is important, is the mechanism to generate the hash for a particular block. So, say now say total of 1000 blocks have been generated, and the next block, that is block number 1001, will be generated. So, this process is called the mining of that block. So, that means, generating the block number 1001 is a mining process, and it is basically the mechanism to generate the hash based on the transactions through its Merkle tree, the previous block's hash and certain other things, so that the hash of this block number 1001, they satisfy the required properties, which is, as we said, is about the number of leading zeros. And how many leading zeros? These are all they are included in the block header itself. We will see very quickly. So, the mechanism of course needs to be complicated enough to make the blockchain tamper proof, as we have said, and this process of Bitcoin mining is basically generating the hash, which is hash of the previous block, which is this HK minus 1, a timestamp, the nonce, that is something that one has to find out, and there are something more, as we will quickly see. So, the problem here is to find the nonce such that HK has the certain predefined complexity in terms of number of leading zeros. And the header also contains mining statistics like these, and part of that is also used in computing the hash of the current blocks. That is what we will very quickly see. So, let us look at this block header, and what we need to see is that we have to understand the notion of difficulty, that we said that there will be certain number of leading zeros. So, that would determine the difficulty of the computation. So, where is that specified? So, if you look at this particular example, that btc.com. So, we have gone to btc.com, and if you see this screen, you will see that there is this notion of bits here. So, which actually tells us what is the complexity. So, here it is written bits is 0x something. Okay. So, that is one of the components, and it is a hexadecimal number. So, a typical example is say 0x denotes that it is a hexadecimal number, and there are 8 such hexadecimal digits, say 170E2632. Here the first byte, that means is 1 and 7. So, each of these is 4 bits. So, 1 and 7, this is 8 bits from the first byte, that is the index, and the next 3 bytes from coefficients. Okay. So, the target, that means the target complexity, that is going to determine how many leading zeros would be there, is this coefficient multiplied by 2 raised to the power 8 into index minus 3. Now, what does it mean in this particular example? That, as we said, that first byte is the index. So, index then is 17 in hex, means it is 23 in decimal, and then these other 3 bytes, which is this 0E2632, that tells us what is the coefficient. And then the difficulty level is computed in this simple form, that if you compute this target as is shown in this particular bullet. So, this is the target. So, for these values, if you get the target and then if you convert that into hex, you will get a certain number of leading zeros. Now, for this one I will show you what these values are. So, if you see this particular example, okay. So, for this 0x170E2632, for this particular value, if we get the target using this simple formula, you will get a value like what is this shown here as this particular value, that is 1.355 something into 10 raised to the power 54. And now, if I convert this number into hex, I get this value. Okay. And this hex, mind it, we have to ensure that it has got this 64 hexadecimal digits, so that there are total of 256 digits. So, we get, if you see that we get certain number of leading zeros. So, in this case what we see here is that we are getting some 15 leading zeros. Okay. So, that means what? That means the block hash that would be generated, it has to be ensured that the hash has 15 leading zeros. Now, if we look at the hash of this particular block for say 703807, I am referring to block number 703807, it can be seen that its block hash is this one, and we see that it has got this many number of leading zeros. So, we see that there are such 16 leading zeros. I am sorry, there are 20, sorry, there are 20 such leading zeros, and of course, what we needed was that there should be at least 19 leading zeros. Okay. So, there are 19 leading zeros based on the current difficulty level, and the block hash that was obtained, that has got 20 leading zeros. So, that minimum requirement of 19 leading zeros, that is satisfied. So, what it means is that it means that we have set a target in terms of the difficulty bits, and then the block hash was generated that satisfied that requirement. So, you see that the cost of mining is very high. For each such block to be mined, a lot of computation power is required to be deployed, so that we finally can come up with a nonce that will result in a hash which has that particular property. Now, what you can do is that you can actually, the steps that I mentioned of converting these particular bits written in hex, which is this one as is mentioned here, and from there getting this one and then converting it to the corresponding hexadecimal representation, you can do using some number conversion utility which is mentioned here. So, you can try out the steps, as I said, you can repeat those steps using any such hexadecimal to decimal and back converter, and one such example is mentioned here. So, the block identifier is the hash of the current block header. These are the hashes that are there in the block header. One is the hash of the current block header, and then there is the Merkle root, the previous block hash as we mentioned to compute the current block, and also the timestamp, previous hash, the Merkle root, and the difficulty bits along with nonce and version. All these are used to compute the current hash. So, this is important that when we are computing the current hash, what we have to do is that we have to use the timestamp, we have to use the previous hash, which is the hash of the previous block kept in the block header of the previous block, the Merkle root, which is based on the current set of transactions in this particular block, the difficulty bit which is specified and which changes over a period of time, it is adjusted for certain reasons which we will talk about later. The nonce is basically the one that one has to come up with, along with the version which is also specified for the current block that is being mined. So, all these are known. So, the timestamp is known, the previous hash is known, the Merkle root is known, the difficulty bits is known, the version number is known, and the process of mining will have to come up with a nonce. So, that all of these when taken together and then hashed, that will result in a hash value that will satisfy the number of leading zeros, which is determined from the difficulty bits that itself is there in this particular block. So, I will show you a quick demonstration, so that you understand what is being done, and then you too can repeat it. So, there are many such block hash verification tools. So, we will use one of those, say this one that I am referring to, and let us go to that particular site, and we will make use of one of these particular blocks. So, let us go to that block hash verification tool which is shown here, and you can see it clearly is that it needs, as you can see, that these 6 different components. Okay. And what are these? So, if we do it for any one of these blocks, so now you see that we are doing it on the fly. So, we are doing it for, say, let us go to btc.com and let us do it for any one of the most recent blocks, so that you will get an idea as to how things work, and it is so really easy to figure out how to get these things done. Okay. So, let us pick up the latest block today, and as you can see, now we have got more blocks created since we started today's lecture itself. So, within this short time, so many new blocks got added. So, let us click on this block number, and then you will see all the information that is required for this process, which is shown here. Let me open that once again. Okay. So, we have this tool. So, what we will do is that for this particular block, which is this okay. So, let us do for this one. So, now if we go to this one, so first we have to enter the version. Okay. So, from where do we get the version? We get the version here. So, if you see here that the version is mentioned here, and then I click this, and then I go to this one and put the version here. So, I paste it here, and then I go back, and then what else I need? I will need the Merkle root. So, I copy the Merkle root. So, I put the Merkle root here, I go back once again, and then I select the number of bits which is the difficulty bits here, and then I have to select the timestamp. So, timestamp we get from here, and we have to get it in UTC format. So, we put the timestamp here, and then all else that we need is the nonce. So, this nonce you see that it has been already calculated. So, we are not calculating the nonce. What we are doing is that we are checking whether indeed the block hash has been computed correctly or not. So, remember that we are not mining the block, we are verifying whether the block has been mined correctly or not. And then the last one is that we need to go to the previous one, which is this 703826 block number, and I copy that, and then I put that here, and I say I calculate block hash. Okay. So, this one calculates the block hash, and then you see that it has got this block hash, okay, which you can see here. And then if you actually look at this particular block that we started with, which is this 703827, you will see that it has got indeed the same as the block hash, which is this so many zeros and this A537, and that is exactly we got here as the output. And then you see that it has got a lot of such leading zeros, and how many leading zeros? That was determined by the value of this difficulty bits. Okay. So, that is the whole concept about verifying whether the block hash has been generated correctly. And there are these other ways of also verifying. There are other sites that you can use. Again, remember that what we showed is that what actually goes in for computing the hash of a particular block, we did not determine the nonce, because that itself is challenging. We did not want to do that, but I wanted to illustrate how one can generate the block hash, and assuming that you have been able to come up with the nonce. The challenge was to actually come up with that nonce. So, to conclude, we have described the structure of a block in a blockchain in today's lecture, and the main components of a block header, how to solve the block generation puzzle. So, we said how to solve means we did not actually solve, because it is computationally very challenging. You need a lot of special hardware for actually doing it, and what is meant by mining of a block. And the references of course are our book on cryptography network security, the blockchain basics, and any other standard textbook on blockchain or Bitcoin you can consult for understanding these concepts. But I would encourage you to repeat what I have done by going through the actual blocks in btc.com or blockchain.com sites, and then using the other site that we mentioned, where you can actually type in or do copy paste of the different components of the header, calculate the hash and check whether it is matching with the actual hash for that particular block. And all this information you are getting on the fly. I showed you how to do it for the very recent one, that means the one that got generated only a few minutes back possibly. So, that brings us to the end of our today's lecture. Thank you very much.